Today we are going to read about the Heisenberg uncertainty principle in chemistry, which is the first year BSc. The second year is in the year as well as and in MSc. This is going to uh, work. So let's start the video lecture without any delay. Of an atomic particle of mass m, if it has to be located within a distance del x, then light with a wavelength of the size of particle should be used to illuminate it. For the particle to be seen, a photon must collide in some way with the particle, for otherwise the photon will be pass right through and the particle will appear transparent. The photon has a momentum p equal h upon lambda, and during the collision during the collision and the particle will appear transparent. The photon has momentum p equal h upon lambda, and during the collision some of the momentum will be transferred to the particle. The very act of locating the particle leads to a change in its momentum. If a particle has to be located more accurately, light of even smaller wavelength should be used. Consequently, the photon in the light beam will have greater momentum, as some of the photon's momentum is referred to the particle in the process of locating. In the momentum change of the particle becomes greater. A careful analysis of this process was carried out by Werner Heisenberg, who showed that it is not possible to determine exactly how much photon momentum is referred to electron. Rather, this means that if a particle has to be located within a region del x, then this causes an uncertainty in momentum of the particle. Heisenberg was able to show that if del p is uncertainty in the momentum, then del x into del p is not greater than h upon voice mistake del x into del p greater than h upon 2 pi. The smaller the del x, the greater and del p, and vice versa, but the product of the two is always given by equation. This amounts that is impossible to measure simultaneously the position and momentum of a particle with arbitrary precision. Such a interpretation may means that the uncertainty relation is responsible for limitations associated with the processes of measurement. One might be led to assume that a microparticle itself possesses a definite coordinate as well as definite momentum, but the uncertainty relation does not permit us to measure them simultaneously. This may be an erroneous conclusion. Thus, uncertainty relation is not the creates certain obstacles to the understanding of micro phenomena, but it reflects certain peculiarities of the objective properties of microparticle. The following two examples demonstrated the numerical consequence of the uncertainty principle. Problem first. Calculate the uncertainty position of the automobile of mass 500 kg moving with a speed of 50 plus minus 0.001 km per hour. Solution. The uncertainty of position is del x equal h upon m del v equal 1.05 into 10 to power minus 34 js upon 5 into 10 to power 2 kg, bracket close bracket, 2.77 into 10 to power minus 4 meter per second equal 7.559 into 10 to power 34 m. This is very small distance and wholly negligible as compared to mass and velocity of the automobile.